Hi everyone, and welcome to Scoring a Model. This is going to be the first video out of a three-part series. I'm going to make one video where we can go through an example of this in Visual Studio, and the third video where I talk about which metric is the most important for certain outcomes you might be trying to accomplish. Not all of these metrics will matter to the same extent depending on the question you're trying to answer. So let's get into the metrics used for scoring a model. When you're training a classification model or you're monitoring your model over time, you'll have to assess how the model is performing. This is done by looking at the precision, the sensitivity, the specificity, negative predictive value, accuracy, and F1 score. If you're training a classification model, the AUC or area under the ROC curve is also incredibly important, but that formula is not something which is easily written out, so I'll leave that out of the video for now. And to better understand this, let's say we have 5 years of diagnosis data, and we're using the first 4 years of data to predict who will be diagnosed with obesity in the last year. So let's break this down. Here, we first start with our actual data, which is going to be labeled as either negative or positive. With our example, those diagnosed in the last year of data with obesity are our negative labels, or excuse me, those not diagnosed in the last year of data with obesity are our negative labels, and those who were diagnosed are our positive labels. And when we run our model, this is going to give us a prediction of whether the model predicts the patient is likely to develop obesity or not. And this usually uses a cutoff of 0.5 by default, with anything below the cutoff becoming a negative prediction and anything above the cutoff becoming a positive prediction. Our true positives are going to be all of the people who our model predicted to develop obesity, and they did. This is where the positive from the actual and the positive from the predicted overlap. The next box where our model again predicted something correctly would be our true negatives. These are the patients who our model said weren't likely to develop obesity, and they didn't develop obesity. The false negatives are going to be those who our model predicted as not developing obesity, but they actually did. This is called a false negative because our model falsely predicted them to be negative. This is also called a type 2 error. The false positives are also ones our model got incorrect, and these are our type 1 errors. These are the ones our model predicted to develop obesity, but they never did. And for our example, let's say these are the predictions our model made. It correctly identified 80 members as developing obesity and 180 members as not developing obesity. It then falsely predicted that 30 members would develop obesity when they didn't, and that 20 members would not develop obesity when they actually did. First, let's look at the sensitivity of the model, which is also called our recall. The formula cares only about those patients who are labeled as developing obesity in our data, so our positives. This looks at the true positives divided by our true positives and false negatives. So in other words, it looks at everyone who actually developed obesity, which ones did our model get right? And when we calculate this, we get a sensitivity or a recall of 0.8, which means that out of all of the members who actually developed obesity, we predicted 80% of them correctly. Next, let's look at the sensitivity. The sensitivity formula only includes those who are negatively labeled or those who didn't actually get diagnosed with obesity within the year. The formula looks at how many of those we predicted correctly. When we calculate the specificity, we get 0.86. This means that out of all members who didn't develop obesity, we correctly predicted 86% of them. Next, let's look at the positive predictive value, which is also called the precision. This formula considers all of those predictions which our model predicted to be positive, or in this case, to develop obesity. And when we take the true positives and divide it by the true and false positives, we get 0.73, which means out of all of the positive predictions our model made to develop obesity, it was correct about 73% of them. Next, the negative predictive value, which is the counterpart to the positive predictive value. This considers all of our negative predictions. Here we're dividing our true negatives by our true negatives and false negatives, which gives us 0.9. This means that for all of the members our model said would not develop obesity, 90% of them were correct, while 10% of them did end up developing obesity. Next is the accuracy. This looks at all predictions our model made and cares about what we got right out of all of our predictions. When looking at everything our model got right, divided by all predictions made, we see that 84% of our predictions were correct. Lastly, we have our F1 score, which takes both recall and precision into account. This looks at the balance between the percent we got right out of everyone who developed obesity and the percent that actually developed obesity out of everyone we predicted to. Here we get an F1 of 0.76, and generally anything above 0.7 is considered good, but it really depends on the project that you're doing. Thank you so much for watching this, and if you enjoyed this video, please like and subscribe for more content like this. And like I said, this is the first part of a 3-part series, and next I'll talk about an example in Visual Studio, and then lastly, which metric is the most useful for what.